What if I told you that right now, as you're watching this video, there's a sleeping giant beneath America that could wipe out human civilization faster than any asteroid from space? While NASA spends billions scanning the skies for killer rocks, the real threat isn't coming from above. It's brewing right beneath Yellowstone National Park. This isn't science fiction. This is geological reality. And by the end of this video, you'll understand why the Yellowstone supervolcano makes every disaster movie look like a children's bedtime story. I'm here at the Sleepy Cosmos to take you on a journey through Earth's most terrifying natural phenomenon. So make sure to subscribe and hit that notification bell, because you won't want to miss what we're about to uncover about the monster hiding in plain sight. When you think of Yellowstone, your mind probably conjures images of pristine wilderness, spouting geysers, and families posing for photos next to bubbling hot springs. What you're actually looking at is one of the most deceptive landscapes on Earth, a thin crustal lid, barely containing a geological monster so powerful that it defies human comprehension. Welcome to the Yellowstone caldera, a supervolcano so massive and so dangerous that it makes Mount Vesuvius look like a backyard firecracker. This isn't just another mountain that happens to have magma inside. This is a fundamentally different beast altogether, one that operates on a scale that challenges everything we think we know about volcanic threats. The first thing you need to understand is that Yellowstone doesn't look like what most people imagine when they hear the word volcano. There's no towering cone-shaped mountain with smoke billowing from its peak. Instead, what we're dealing with is something far more insidious, a massive depression in the Earth's crust called a caldera, stretching an almost incomprehensible 34 miles by 45 miles across. To put that in perspective, you could fit the entire city of Los Angeles inside this caldera with room to spare. But even these staggering surface dimensions pale in comparison to what's happening beneath our feet. Deep below this deceptively peaceful landscape lies a magma chamber that exists on a scale that's difficult for the human mind to process. Picture an underground ocean of molten rock, roughly 55 miles long and 20 miles wide, reaching depths of up to 9 miles in some locations. The sheer volume of magma contained within this chamber is estimated at around 15,000 cubic miles, enough liquid rock to fill the entire Grand Canyon 11 times over. This isn't some distant theoretical construct buried impossibly deep in the Earth's core. This is a very real, very active reservoir of molten material sitting just a few miles beneath the surface, constantly shifting, heating, and building pressure like a pressure cooker that's been left on the stove for hundreds of thousands of years. What makes this geological situation even more extraordinary is the type of magma we're dealing with. Unlike the relatively fluid basaltic lava you might see flowing from Hawaiian volcanoes, Yellowstone's magma is predominantly rhyolitic, an incredibly thick, sticky, silica-rich composition that's loaded with dissolved gases. Think of the difference between honey and water. When Hawaiian lava erupts, it flows relatively gently, allowing gases to escape gradually. But rhyolitic magma is like trying to force honey through a straw. It builds up tremendous pressure because the thick consistency prevents gases from escaping easily. When this type of magma finally does erupt, it doesn't flow gently down mountainsides. It explodes with the force of thousands of nuclear weapons, hurling billions of tons of material high into the atmosphere at velocities that can reach hundreds of miles per hour. The geological forces at work here are being driven by something even more incredible: the Yellowstone hotspot. Far beneath the North American continent, approximately 400 miles down in the Earth's mantle, there exists what geologists call a mantle plume. This is essentially a column of superheated rock that rises from deep within our planet like a blowtorch flame, carrying temperatures exceeding 2,000 degrees Fahrenheit. This plume has been burning its way upward through the Earth's interior for millions of years, and when it finally reaches the base of the continental crust, it begins to melt everything in its path. The resulting magma, being less dense than the solid rock around it, rises toward the surface, accumulating in this massive underground chamber that we now call the Yellowstone Magma Reservoir. But here's where the story gets even more fascinating and terrifying. The North American continental plate is constantly moving southwest at a rate of about 2 inches per year over this stationary hotspot. It's like moving a piece of paper over a candle flame. As the continent drifts, the hotspot burns through different locations, creating a trail of ancient calderas stretching across southern Idaho like a geological breadcrumb trail. The Snake River Plain, that distinctive curved depression cutting across Idaho, is actually a scar left by this same hotspot as it burned through the landscape over the past 16 million years. Yellowstone represents the current location where this deep earth blowtorch is focused, and the evidence of its power is written across the landscape in ways that most visitors never recognize. The caldera itself tells a story of almost unimaginable violence. What appears to be a gentle depression surrounded by mountains is actually a collapsed crater formed when the ground literally fell into the emptied magma chamber during the last major eruption 640,000 years ago. Imagine an underground cavern the size of Rhode Island suddenly emptying its contents into the atmosphere. The overlying rock had nowhere to go but down, creating this massive sunken feature. The rim of this ancient collapse is still visible today as a roughly circular arrangement of mountains and ridges. But most visitors driving through the park have no idea they're traveling across the floor of one of the most dangerous volcanic features on the planet. The thermal features that make Yellowstone famous, the geysers, hot springs, mud pots, and fumaroles, are essentially pressure relief valves for this massive heat source below. Old Faithful isn't just a charming natural curiosity. It's a direct connection to the magma chamber, a window into the incredible thermal energy being generated just a few miles beneath the surface. The fact that over 10,000 hydrothermal features exist within the park boundaries should tell us something profound about the scale of the heat source below. The water shooting from these geysers can reach temperatures of nearly 200 degrees Fahrenheit, and that's after it's traveled miles through underground plumbing systems, cooling along the way. The source temperature deep below is far, far hotter. What makes this situation particularly unnerving is that the magma chamber isn't static. It's constantly evolving, shifting, and changing. Advanced seismic imaging has revealed that this underground reservoir exists in multiple layers, with different zones containing magma at various stages of crystallization. Some areas contain mostly liquid magma ready to erupt, while others hold a crystal mush that could be remobilized under the right conditions. The chamber is also constantly being recharged with fresh magma from the mantle plume below, like a bathtub with the faucet running while the drain is mostly plugged. Recent scientific discoveries have made the picture even more complex and concerning. In 2015, researchers using advanced seismic tomography discovered that the Yellowstone magma system is actually even larger than previously thought, extending much deeper into the Earth's crust. They found evidence of a secondary magma reservoir beneath the primary chamber, containing an additional 11,000 cubic miles of molten and semi-molten rock. This lower chamber appears to be where magma from the deep mantle plume first accumulates before rising into the shallower reservoir that feeds the surface thermal features. The implications are staggering. We're not just dealing with one massive magma chamber, but with a complex multi-level system that's even larger and more powerful than scientists previously realized. Perhaps most unsettling of all is the realization that this entire system is showing signs of ongoing activity. The Yellowstone caldera isn't some ancient dormant feature slowly cooling down over geological time. It's alive, it's active, and it's constantly reminding us of its presence through subtle but measurable changes in the landscape above. Between 2004 and 2014, portions of the caldera floor rose by nearly 6 inches, a rate of ground deformation that's considered extremely rapid in geological terms. It's as if the giant below is stirring in its sleep, and every movement sends ripples through the landscape above. This ground deformation isn't random. It appears to be directly related to changes in the pressure and volume of the magma chamber below, suggesting that the system is actively evolving and potentially building towards some future state of instability. The more we learn about Yellowstone's geological plumbing system, the more we realize that we're dealing with something that operates on a scale and timeline that dwarfs human experience. This isn't just a volcano. It's a geological superstructure that's been building and rebuilding itself for millions of years, powered by forces from deep within our planet that will continue long after human civilization has become a footnote in Earth's history. The fact that we've built our modern society on top of and around features like this, often without fully comprehending their true nature and potential, says something profound about both our remarkable adaptability as a species and our sometimes dangerous tendency to assume that the ground beneath our feet will always remain stable and predictable. Hollywood has trained us to fear the skies, filling our nightmares with images of massive asteroids streaking through space toward an inevitable collision with Earth. The scenario is undeniably terrifying. A mountain-sized rock traveling at tens of thousands of miles per hour, carrying the kinetic energy of billions of nuclear weapons, capable of ending civilization in a single catastrophic moment. But while we've become experts at scanning the heavens for these cosmic threats, we've largely ignored a far more insidious danger that's been lurking beneath our feet all along. The brutal truth is that supervolcanic eruptions represent a fundamentally different and arguably more dangerous class of existential threat than asteroid impacts, and understanding why requires us to completely reimagine how we think about planetary catastrophes. The most famous asteroid impact in Earth's history occurred 66 million years ago, when a 6-mile-wide chunk of rock and metal slammed into what is now the Yucatan Peninsula with the force of roughly 10 billion Hiroshima bombs. The Chicxulub impact, as it's known to scientists, excavated a crater over 90 miles wide and sent shock waves around the globe that triggered earthquakes, tsunamis, and wildfires on a planetary scale. The immediate devastation was apocalyptic. Everything within hundreds of miles of the impact site was instantly vaporized or incinerated, while the rest of the planet was subjected to a rain of molten debris that turned the sky into a furnace. But here's the crucial difference that most people don't understand. This entire cataclysmic event unfolded over a matter of hours or days. It was sudden, violent, and mercifully brief. A supervolcanic eruption operates on an entirely different timeline and follows a completely different playbook of destruction. When Yellowstone eventually awakens from its 640,000-year slumber, it won't announce itself with a brilliant flash of light streaking across the sky. Instead, it will begin with subtle warning signs that could unfold over weeks, months, or even years. Increased seismic activity, changes in thermal features, ground deformation that accelerates beyond what scientists consider normal background levels. But once the eruption begins in earnest, it won't be over in a few hours, like an asteroid impact. A major supervolcanic eruption can continue for months or even years, pumping massive quantities of ash, gas, and debris into the atmosphere in a sustained assault on the planet's climate system that makes asteroid impacts look almost gentle by comparison. The energy scales involved in these two types of catastrophes reveal just how fundamentally different they are. The Chicxulub asteroid released an estimated 100 trillion tons of TNT equivalent energy in a single instant, a number so large it's almost meaningless to human comprehension. But the last major Yellowstone eruption, the Lava Creek event 640,000 years ago, ejected roughly 240 cubic miles of material into the atmosphere over an extended period. To put this in perspective, that's enough volcanic debris to bury the entire state of Texas under 3 feet of ash and rock. The sustained energy output of such an eruption, while perhaps not exceeding the instantaneous energy release of a major asteroid impact, represents a prolonged bombardment of the Earth's atmospheric and climate systems that can persist for years rather than hours. But the real difference lies in what happens after the initial impact or eruption begins. When the Chicxulub asteroid struck Earth, it certainly triggered massive climate changes. The impact winter that followed likely contributed to the extinction of non-avian dinosaurs and countless other species. However, this climate disruption was primarily caused by debris and dust thrown up by the impact itself, material that eventually settled out of the atmosphere over months to years. The Earth's climate system, while severely disrupted, eventually returned to something resembling normal conditions. Ecosystems recovered, evolution continued, and life found ways to adapt and thrive in the post-impact world. Supervolcanic eruptions create a far more complex and long-lasting assault on planetary climate systems. Unlike asteroid impacts, which primarily inject rocky debris and water vapor into the atmosphere, volcanic eruptions pump massive quantities of sulfur dioxide and other gases into the stratosphere along with the ash and debris. This sulfur dioxide undergoes chemical reactions in the upper atmosphere, forming sulfuric acid aerosols that can remain suspended for years, creating a reflective haze that bounces sunlight back into space. The 1991 eruption of Mount Pinatubo in the Philippines, which was relatively tiny compared to a Yellowstone-scale event, injected enough sulfur dioxide into the stratosphere to cool global temperatures by about 0.5 degrees Celsius for 2 years. A full-scale Yellowstone eruption would be roughly 1,000 times more powerful than Pinatubo, potentially triggering a volcanic winter that could last for decades. The predictability factor represents another crucial difference between these two types of threats. Our asteroid detection systems have become remarkably sophisticated over the past few decades. Organizations like NASA's Planetary Defense Coordination Office continuously scan the skies using ground-based telescopes and space-based observatories, cataloging every potentially hazardous object larger than about 450 feet in diameter. We now know the locations and orbital paths of virtually every asteroid large enough to cause significant regional or global damage, and we can predict their movements with extraordinary precision centuries into the future. More importantly, we're developing the technology to actually do something about asteroid threats. Missions like DART have demonstrated that we can alter the trajectory of incoming objects given sufficient warning time. Supervolcanoes, on the other hand, operate according to their own inscrutable timeline. Despite decades of intensive monitoring and research, scientists still cannot predict with any meaningful precision when Yellowstone might erupt. We can measure seismic activity, track ground deformation, analyze gas emissions, and monitor thermal changes. But translating these observations into reliable eruption forecasts remains one of the most challenging problems in Earth sciences. The geological processes that lead up to supervolcanic eruptions unfold over timescales that don't align well with human planning horizons. Warning signs might appear decades before an eruption, or they might only become apparent weeks or months in advance. Even more troubling, some of the activities we can measure, like the ground deformation that has occurred at Yellowstone over the past 2 decades, could represent normal background variations in an active volcanic system rather than precursors to an imminent eruption. The technological solutions available for dealing with these two threats also differ dramatically. While deflecting or destroying an incoming asteroid remains an enormously challenging engineering problem, it's at least theoretically within the realm of possibility using current or near-future technology. We can imagine scenarios involving nuclear weapons, kinetic impactors, gravity tractors, or other exotic propulsion systems that could alter an asteroid's trajectory enough to make it miss Earth entirely. The physics are well understood, even if the engineering challenges remain formidable. But what do you do about a supervolcano? Unlike asteroids, which exist in the vacuum of space where the laws of orbital mechanics provide clear guidelines for intervention, supervolcanoes are integrated into the complex geological systems of our planet in ways that make direct intervention essentially impossible. Some scientists have proposed ambitious geoengineering schemes, such as drilling into the Yellowstone magma chamber to release pressure gradually, or installing massive geothermal energy extraction systems to cool the magma reservoir. However, these ideas remain largely theoretical, and many experts worry that such interventions could actually trigger the very eruption they're intended to prevent. When you're dealing with a system containing thousands of cubic miles of pressurized molten rock, there's very little room for error in any intervention attempt. The recovery timeline from these two types of disasters also reveals fundamental differences in their long-term impact on human civilization. Asteroid impacts, despite their immediate devastation, create relatively straightforward recovery scenarios. The debris settles, the dust clears, and the primary challenge becomes rebuilding infrastructure and dealing with the ecological disruption. The impact crater becomes a permanent scar on the landscape, but the rest of the planet can begin returning to normal relatively quickly. Archaeological evidence suggests that human populations have successfully survived and recovered from major volcanic events in the past. But these were regional disasters affecting limited geographical areas. A Yellowstone-scale supervolcanic eruption would create recovery challenges that dwarf anything in recorded human history. The volcanic winter effect could persist for years or decades, making agriculture impossible across vast regions of the planet. Unlike an asteroid impact, which primarily affects the impact site and surrounding areas, a supervolcanic eruption has the potential to disrupt weather patterns, growing seasons, and ecological systems on every continent simultaneously. The ash fallout alone would create logistical nightmares that could persist for decades. Volcanic ash doesn't simply wash away like normal dust, but forms a concrete-like substance when mixed with water, clogging drainage systems, destroying machinery, and making large areas essentially uninhabitable until extensive cleanup efforts can be completed. Perhaps most importantly, the frequency of these threats tells a story that should fundamentally reshape how we think about existential risks. Truly, civilization-ending asteroid impacts occur roughly once every 100 million years on average, making them extremely rare events on human timescales. Yellowstone-scale supervolcanic eruptions, however, occur much more frequently, roughly every 600,000 to 800,000 years based on the geological record. We're currently about 640,000 years since the last major Yellowstone eruption, putting us well within the statistical window when another eruption could occur. While this doesn't mean an eruption is imminent, it does suggest that supervolcanic threats are far more likely to affect human civilization within any given time frame than asteroid impacts of comparable destructive power. Standing at any viewpoint within Yellowstone National Park, most visitors see pristine wilderness, dramatic landscapes, and perhaps the occasional bison wandering through a meadow. What they're actually witnessing is one of the most deceptive geological features on Earth. A massive volcanic crater so large that you can't see its edges from any single vantage point. So ancient that forests have grown over its scars, and so powerful that it represents one of the most dangerous geological structures on the planet. The Yellowstone caldera isn't just a depression in the ground. It's a window into the violent history of our planet and a preview of the catastrophic forces that continue to churn beneath our feet, waiting for their next opportunity to reshape the face of North America. To truly understand the Yellowstone caldera, we need to reimagine our concept of what a volcanic crater can be. Most people think of volcanic craters as relatively small, circular depressions at the top of cone-shaped mountains, the classic image of a volcano with a smoking crater at its peak. But calderas operate on an entirely different scale and form through completely different mechanisms. The Yellowstone caldera measures approximately 34 miles by 45 miles across, making it larger than the entire state of Rhode Island. This isn't a crater formed by a simple volcanic explosion. It's a collapse feature created when the ground literally fell into an emptied underground magma chamber, like a massive sinkhole, but on a scale that defies human comprehension. The formation of this caldera represents one of the most violent geological events in Earth's recent history. About 640,000 years ago, the pressure building in Yellowstone's underground magma chamber reached a critical threshold, triggering what scientists call the Lava Creek eruption. This wasn't a typical volcanic eruption with lava flowing down mountainsides. This was a cataclysmic explosion that ejected roughly 240 cubic miles of molten rock, ash, and gases into the atmosphere, with the force of thousands of nuclear weapons detonating simultaneously. To put this volume in perspective, imagine every building in Manhattan, from the smallest apartment to the tallest skyscraper, reduced to rubble and debris. Then multiply that by several thousand times. That's roughly the amount of material that was blasted out of the Earth in a matter of days or weeks. But the truly mind-boggling part of this story is what happened next. Once the magma chamber had expelled this enormous volume of material, it created a vast underground cavern, essentially a hollow space beneath the Earth's surface the size of a major metropolitan area. The overlying rock, suddenly unsupported by the magma that had been holding it up, had nowhere to go but down. The collapse was catastrophic and nearly instantaneous in geological terms, creating a depression that dropped as much as 1,500 feet below the surrounding landscape. This collapse didn't happen gently. It would have triggered massive earthquakes and landslides as billions of tons of rock crashed into the emptied magma chamber below. The rim of this ancient collapse is still visible today, though most visitors don't recognize it for what it is. The roughly circular arrangement of mountains and ridges that surround the central portion of Yellowstone, including Mount Washburn, the Gallatin Range, and the Absaroka Range, represent the walls of this massive crater. These aren't separate mountain ranges that happen to form in a circle. They're the remnants of the landscape that existed before the caldera collapse, now standing as monuments to one of the most powerful geological events in recent Earth history. When you drive from West Yellowstone toward Old Faithful, you're actually descending into this ancient crater, traveling across ground that once stood hundreds of feet higher before it collapsed into the void below. What makes the Yellowstone caldera even more fascinating is that it's actually just the most recent in a series of massive calderas that have formed in this region over the past 2 million years. Advanced geological mapping has revealed the remains of at least 2 earlier calderas underlying and surrounding the current one. The Huckleberry Ridge caldera, formed by an eruption 2.1 million years ago, was even larger than the current Yellowstone caldera, stretching nearly 60 miles across. The Mesa Falls caldera, created 1.3 million years ago, overlaps with both the older and younger calderas, creating a complex nested structure of overlapping collapse features that speaks to the incredible longevity and persistence of the volcanic forces at work in this region. This nested caldera structure tells us something profound about the nature of the Yellowstone system. This isn't a one-time geological event, but rather an ongoing cycle of magma accumulation, eruption, and collapse that has been repeating for millions of years. Each eruption empties a portion of the underground magma reservoir, causing the overlying ground to collapse and form a caldera. Over time, continued magma injection from the deep mantle plume refills the chamber. The collapsed area gradually bulges upward as pressure builds, and the cycle begins anew. We're currently living during the recharge phase of this cycle, watching as the Yellowstone magma chamber slowly refills and builds pressure for whatever comes next. The floor of the current caldera tells its own remarkable story of geological violence and recovery. Rather than being a simple bowl-shaped depression, the caldera floor is characterized by 2 distinctive bulges known as resurgent domes, the Mallard Lake Dome and the Sour Creek Dome. These elevated areas rise several hundred feet above the surrounding caldera floor and represent places where magma intrusion from below has pushed the collapsed ground back upward. It's as if the Earth is trying to heal the wound created by the last eruption, but the forces responsible for that eruption are still active, still pushing upward, still building towards some future release of energy that could dwarf the events that created the caldera in the first place. Advanced geophysical surveys have revealed that these resurgent domes aren't just static features left over from ancient geological processes. They're actively changing, rising, and falling over periods of years to decades in response to changes in the magma chamber below. Between 2004 and 2014, parts of the caldera floor rose by nearly 6 inches, a rate of ground deformation that's considered extremely rapid in geological terms. This movement isn't random. It appears to be directly correlated with changes in the volume and pressure of the magma reservoir beneath the caldera, suggesting that we're witnessing the real-time evolution of one of the world's most dangerous volcanic systems. The hydrothermal features that make Yellowstone famous, the geysers, hot springs, mud pots, and fumaroles scattered throughout the park, are intimately connected to the caldera structure and provide a constant reminder of the incredible heat source lurking just beneath the surface. These features aren't randomly distributed across the landscape. They follow clear patterns that reflect the underlying geology of the caldera system. The highest concentration of thermal features occurs along the caldera rim and within the caldera itself, marking the places where the fractured and collapsed rock provides pathways for superheated water to reach the surface. Old Faithful, perhaps the most famous geyser in the world, sits directly on the edge of one of the resurgent domes, its regular eruptions serving as a sort of geological heartbeat that reflects the ongoing thermal activity in the magma chamber below. But the Yellowstone caldera is remarkable not just for its size and violent history, but also for what it reveals about the deep structure of our planet. The formation of this caldera required the accumulation of enormous volumes of magma in a relatively shallow crustal reservoir, which in turn required a sustained heat source capable of melting solid rock over periods of hundreds of thousands of years. This heat source is the Yellowstone hotspot, a mantle plume that originates from depths of 400 miles or more within the Earth's interior and has been burning its way through the North American continent for over 16 million years. The caldera represents the current surface expression of this deep-seated thermal anomaly, a window into processes that operate on scales of time and space that challenge human comprehension. Recent scientific advances have revealed that the Yellowstone caldera is even more complex than previously understood. High-resolution seismic imaging has shown that the magma chamber beneath the caldera exists as a complex multi-level system with different zones containing magma at various stages of crystallization and different temperatures. Some areas contain mostly liquid magma that could potentially erupt, while others hold a crystal-rich mush that would need to be remobilized by fresh magma injection before it could participate in an eruption. This complexity means that the caldera isn't simply sitting on top of a giant balloon of liquid rock waiting to pop. It's connected to a sophisticated plumbing system that extends deep into the Earth's crust and mantle. The ongoing monitoring of the Yellowstone caldera represents one of the most intensive geological surveillance operations on Earth. An array of seismometers continuously records the thousands of small earthquakes that occur within the caldera each year, providing real-time information about stress changes and magma movement in the subsurface. GPS stations measure ground deformation with millimeter precision, tracking the subtle rise and fall of the caldera floor as it responds to changes in the magma chamber below. Gas sensors monitor the composition and emission rates of gases escaping from thermal features, looking for chemical signatures that might indicate changes in the magma system. Satellite imagery provides a bird's-eye view of thermal changes and ground deformation across the entire caldera, while gravity measurements can detect changes in the density of subsurface materials that might indicate magma movement. Despite all this sophisticated monitoring, the Yellowstone caldera remains fundamentally unpredictable in its behavior. The geological processes that could lead to another catastrophic eruption operate on timescales that don't align well with human observation periods, and the complex interactions between magma chemistry, crustal stress, and external triggering factors make it extremely difficult to forecast when or if the next major eruption might occur. What we do know is that the caldera represents an active, evolving geological system that continues to pose significant risks not just to the local region, but potentially to global climate and human civilization as a whole. The story of Yellowstone's violent past reads like a geological horror novel, with each chapter more terrifying than the last. Over the past 2.1 million years, this seemingly peaceful corner of Wyoming has been the stage for three apocalyptic eruptions so powerful they fundamentally altered the landscape of North America and influenced global climate patterns for decades or centuries afterward. But here's what should keep you awake at night. Geological evidence suggests that each successive eruption has been more powerful than the one before it, and we're currently living in the longest quiet period between eruptions in Yellowstone's recorded history. To understand what might be coming, we need to journey back through time and examine the archaeological record of destruction that this supervolcano has left carved into the very rocks beneath our feet. The oldest and most catastrophic eruption in Yellowstone's known history occurred 2.1 million years ago, creating what geologists now call the Huckleberry Ridge Tuff. This eruption was so monumentally destructive that it defies easy comparison to anything in recorded human experience. The event ejected an estimated 2,450 cubic kilometers of magma, ash, and debris into the atmosphere. That's roughly 588 cubic miles of material, enough to bury the entire state of Texas under nearly 3 feet of volcanic debris. To put this in perspective, this single eruption expelled more material than all the volcanic activity recorded in human history combined, multiplied by several hundred times. The ash cloud from this eruption was so massive that it darkened skies across most of North America for months, with ash deposits found as far away as the Gulf of Mexico and the Atlantic seaboard. The pyroclastic flows generated by the Huckleberry Ridge eruption traveled outward from the source at speeds exceeding 100 miles per hour, consisting of superheated gas and rock fragments at temperatures over 1,000 degrees Fahrenheit. These flows were so hot and fast-moving that they instantly incinerated everything in their path, leaving behind a thick layer of welded volcanic rock called tuff that can still be seen today in road cuts and canyon walls throughout the region. The sheer volume of material ejected during this eruption was so enormous that it created a caldera nearly 60 miles across, significantly larger than the current Yellowstone caldera. This ancient crater was so vast that early geologists didn't recognize it as a single volcanic feature, instead interpreting the rim mountains as separate geological formations until sophisticated mapping techniques revealed the truth about their common origin. The climatic effects of the Huckleberry Ridge eruption would have been globally catastrophic. The massive injection of sulfur dioxide and ash into the stratosphere would have created a volcanic winter lasting for years, dropping global temperatures by several degrees and disrupting weather patterns across the planet. This occurred during a critical period in human evolution, when our early ancestors were just beginning to develop the cognitive and technological capabilities that would eventually lead to modern civilization. While we can only speculate about the impact on early human populations, the eruption certainly would have caused mass extinctions among plant and animal species across North America, fundamentally reshaping the continent's ecosystems in ways that influenced evolutionary pathways for millions of years afterward. The second major eruption, known as the Mesa Falls event, occurred 1.3 million years ago and was only slightly less catastrophic than its predecessor. This eruption ejected approximately 280 cubic kilometers of material, creating a caldera that overlapped with the earlier Huckleberry Ridge structure. What makes the Mesa Falls eruption particularly interesting to scientists is that it provides evidence of how the Yellowstone system can produce massive eruptions even while still recovering from previous events. The magma chamber had not fully recharged to its previous volume, yet it still managed to generate an eruption powerful enough to affect continental-scale climate patterns and deposit ash across thousands of square miles. The geological deposits left by the Mesa Falls eruption tell a story of incredible violence and devastation. The eruption began with massive Plinian columns, towering fountains of gas, ash, and volcanic debris that rose high into the stratosphere before collapsing back to Earth in devastating pyroclastic flows. These flows moved across the landscape like fluid avalanches of superheated rock and gas, following valleys and low-lying areas, but also climbing over hills and ridges with enough momentum to surmount topographic barriers hundreds of feet high. The resulting deposits, known as the Mesa Falls Tuff, can be traced across much of southern Idaho and northern Utah, providing a permanent geological record of the eruption's incredible reach and power. But it's the most recent eruption, the Lava Creek event that occurred 640,000 years ago, that created the Yellowstone landscape we know today and provides the most detailed picture of what a future eruption might look like. This eruption ejected approximately 1,000 cubic kilometers of material, less than the two previous eruptions, but still representing one of the most powerful volcanic events in Earth's recent geological history. The Lava Creek eruption created the current Yellowstone caldera and distributed ash across much of the western United States, with deposits found as far east as the Mississippi River and as far south as northern Mexico. What makes the Lava Creek eruption particularly well studied is the preservation of its deposits and the wealth of geological evidence it left behind. The eruption sequence began with the formation of massive eruption columns that rose 25 to 35 miles into the atmosphere, high enough to inject material directly into the stratosphere where it could influence global climate patterns. As these columns became unstable and began to collapse, they generated pyroclastic flows that raced across the landscape at speeds exceeding 100 miles per hour, carrying temperatures hot enough to melt copper. These flows filled valleys, climbed over ridges, and traveled more than 60 miles from their source, leaving behind deposits of welded tuff that in some places are more than 400 feet thick. The environmental impact of the Lava Creek eruption extended far beyond the immediate blast zone. Ash fall from the eruption covered an area of roughly 1.5 million square miles. That's about half the area of the continental United States. In areas within a few hundred miles of Yellowstone, the ash accumulation was measured in feet rather than inches, creating a lunar-like landscape where virtually nothing could survive. Even at distances of over 1,000 miles from the source, ash deposits several inches thick would have been sufficient to kill vegetation, contaminate water supplies, and make large areas temporarily uninhabitable for both humans and animals. The pattern of ash distribution from the Lava Creek eruption provides crucial insights into how a future Yellowstone eruption might affect modern North America. The prevailing westerly winds carried the bulk of the ash eastward, with the heaviest deposits concentrated in areas that are now some of the most productive agricultural regions in the United States. States like Nebraska, Kansas, Iowa, and Missouri, currently responsible for producing much of America's corn, wheat, and livestock, received ash deposits that would have made agriculture impossible for years or decades after the eruption. The economic and social implications of such widespread agricultural disruption in today's interconnected world would be absolutely catastrophic. Perhaps most unsettling is the evidence that Yellowstone's eruptions are becoming more powerful over time, not less. While volcanic systems typically become less explosive as they mature and their magma chambers cool, Yellowstone appears to be following the opposite trend. The increasing power of successive eruptions suggests that the deep mantle plume feeding the system is becoming more efficient at generating and accumulating magma, or that changes in the crustal structure above the plume are allowing for the buildup of larger and more volatile magma reservoirs. This trend implies that a future eruption could potentially be even more devastating than the already catastrophic events of the past. The geological record also reveals that the intervals between major eruptions are highly variable, ranging from roughly 600,000 to 800,000 years. We're currently about 640,000 years since the last major eruption, putting us well within the statistical window when another catastrophic event could occur. However, these numbers represent statistical averages rather than predictable cycles, and the complex geological processes that control eruption timing make it impossible to forecast when the next event might happen with any meaningful precision. Recent scientific research has uncovered additional layers of complexity in Yellowstone's eruptive history. Between the three major caldera-forming eruptions, the volcanic system has produced dozens of smaller but still significant eruptions, including large lava flows and smaller explosive events. Some of these intermediate eruptions were powerful enough to affect regional climate and ecosystems, even though they didn't create new calderas or deposit ash across continental distances. This pattern suggests that Yellowstone doesn't simply alternate between periods of complete dormancy and catastrophic eruption, but rather maintains a more continuous level of activity that periodically escalates to truly devastating levels. The preservation of Yellowstone's geological record provides scientists with an unprecedented opportunity to study the long-term behavior of supervolcanic systems. Ice core data from Greenland and Antarctica shows clear chemical signatures from past Yellowstone eruptions, allowing researchers to study their global climate impacts in extraordinary detail. These records reveal that major Yellowstone eruptions have consistently triggered volcanic winters lasting multiple years, with global temperature drops of 1 to 3 degrees Celsius and disruptions to precipitation patterns that affected agriculture and ecosystems worldwide. Understanding this history of destruction isn't just an academic exercise. It's a crucial component of assessing the risks that Yellowstone poses to modern civilization. The geological record makes it clear that major eruptions are not a matter of if, but when, and that each successive eruption has the potential to be more powerful than those that came before. As we continue to monitor the subtle signs of activity within the current caldera system, we're essentially watching the early stages of what could eventually become the next chapter in this ongoing story of geological violence. To truly understand the existential threat that the Yellowstone supervolcano poses to human civilization, we need to examine the most terrifying case study in our planet's recent history, an event so catastrophic that it nearly erased our species from existence entirely. 74,000 years ago, on what is now the Indonesian island of Sumatra, the Toba supervolcano erupted with such devastating force that it pushed humanity to the very brink of extinction. This wasn't just another natural disaster that affected a particular region or continent. This was a global catastrophe that fundamentally altered Earth's climate for decades and reduced the entire human population to perhaps as few as 3,000 to 10,000 breeding pairs worldwide. The Toba catastrophe serves as our most chilling preview of what could happen when Yellowstone eventually awakens, and the parallels between these two supervolcanic systems should terrify anyone who truly understands the implications. The Toba eruption was a monster, even by supervolcanic standards, ejecting an estimated 2,800 cubic kilometers of magma, ash, and debris into the atmosphere, making it roughly 3 times more powerful than the most recent Yellowstone eruption and comparable in scale to Yellowstone's largest historical event, the Huckleberry Ridge eruption 2.1 million years ago. But unlike Yellowstone's ancient eruptions, which occurred long before modern humans existed, Toba erupted at a crucial moment in our species' development. Our ancestors had already evolved into anatomically modern humans and had begun spreading across Africa, the Middle East, and parts of Asia. They had developed sophisticated tool-making capabilities, complex social structures, and the cognitive abilities that would eventually lead to art, language, and civilization. In evolutionary terms, they were recognizably us, and they came terrifyingly close to complete extinction. The immediate impact of the Toba eruption was apocalyptic in scale. The explosion created a caldera 62 miles long and 17 miles wide, instantly vaporizing everything within hundreds of miles of the eruption site. But the local destruction, devastating as it was, represented only the opening act of a global catastrophe that would unfold over the following years and decades. The eruption column rose more than 50 miles into the atmosphere, punching through the stratosphere and injecting massive quantities of sulfur dioxide, ash, and volcanic gases into the upper atmosphere where they could circulate around the entire planet. Within weeks, the Earth was shrouded in a volcanic haze so thick that it blocked substantial amounts of sunlight from reaching the surface, triggering what scientists call a volcanic winter. The climate effects of the Toba eruption were swift and merciless. Global temperatures dropped by an estimated 3 to 5 degrees Celsius, with some regions experiencing temperature drops of up to 15 degrees Celsius. This might not sound like much to someone thinking about daily weather variations, but in terms of global climate systems, these temperature changes were absolutely catastrophic. The drop in global temperature was sufficient to trigger the formation of ice sheets in northern latitudes and cause widespread drought and ecosystem collapse in tropical regions. The volcanic winter lasted for approximately 6 years, followed by a longer period of climate instability that persisted for decades as the Earth's atmospheric and oceanic systems struggled to return to normal patterns. The impact on global ecosystems was nothing short of devastating. Plants across the planet began dying en masse as reduced sunlight made photosynthesis increasingly difficult. Forests that had taken centuries to establish withered and died within years, creating vast landscapes of dead vegetation that provided little food or shelter for the animals that depended on them. The collapse of plant communities triggered cascading effects throughout food webs as herbivores starved and the carnivores that depended on them faced their own survival crises. Marine ecosystems were equally devastated as reduced sunlight killed phytoplankton, the microscopic organisms that form the base of oceanic food chains and produce much of the oxygen in our atmosphere. For our human ancestors, the Toba catastrophe represented an existential crisis unlike anything our species had ever faced. The humans living in Southeast Asia, closest to the eruption site, were almost certainly completely wiped out by the immediate effects of the explosion and subsequent ashfall. But even populations thousands of miles away found themselves struggling to survive in a world that had suddenly become hostile to life itself. The plants and animals they depended on for food began disappearing. Water sources became contaminated with volcanic ash, and the dramatic climate changes made traditional survival strategies ineffective or impossible. The genetic evidence for this near-extinction event is written into the DNA of every person alive today. Population geneticists studying human genetic diversity have discovered what they call a genetic bottleneck that occurred approximately 70,000 to 75,000 years ago, exactly coinciding with the timing of the Toba eruption. This bottleneck represents a dramatic reduction in human genetic diversity that could only have been caused by a severe reduction in population size. The analysis suggests that the entire human population may have been reduced to as few as 3,000 to 10,000 individuals capable of reproduction, a population so small that our species came perilously close to joining the countless other species that have vanished from Earth's history. Different human populations responded to the Toba crisis in various ways, and these responses shaped the future of our species in profound ways. Some groups may have survived by retreating to refugia, small pockets of relatively favorable habitat, where microclimates or geographic features provided some protection from the worst effects of the volcanic winter. Coastal areas with access to marine resources may have been particularly important, as ocean-based food webs were somewhat more resilient than terrestrial ones. Other groups may have survived through behavioral innovations, developing new technologies or social strategies that allowed them to extract resources from increasingly barren landscapes. The recovery period following the Toba catastrophe was slow and uncertain, stretching across multiple generations as human populations gradually rebuilt their numbers and adapted to the changed world around them. This recovery wasn't simply a matter of population growth. It required fundamental changes in human behavior, technology, and social organization. The survivors had to develop new strategies for finding food in depleted landscapes, new technologies for dealing with changed environmental conditions, and new social structures for maintaining group cohesion during times of extreme scarcity. Some researchers argue that the pressures of surviving the Toba catastrophe may have accelerated human cultural and technological development, forcing innovations that wouldn't have occurred under more favorable conditions. The Toba event also provides crucial insights into how modern human civilization might respond to a similar catastrophe today. Our ancestors who survived Toba were scattered hunter-gatherer populations with relatively simple technologies and social structures. They were accustomed to environmental variability and had survival skills that allowed some of them to adapt to drastically changed conditions. Modern human civilization, by contrast, is characterized by enormous population densities, complex technological systems, and an almost complete dependence on industrial agriculture and global supply chains. We've gained incredible capabilities in terms of technology and organization, but we've also become far more vulnerable to disruptions of the natural systems that support our civilization. The agricultural implications of a Toba scale event today would be absolutely catastrophic. Modern agriculture depends on predictable weather patterns, stable temperatures, and adequate sunlight for photosynthesis. A volcanic winter lasting even a few years would cause widespread crop failures across the globe, triggering famines that could affect billions of people. Our highly specialized and interconnected food production systems would be particularly vulnerable, as the failure of key agricultural regions could trigger cascading shortages throughout global supply chains. Unlike our hunter-gatherer ancestors, who could potentially find alternative food sources in wild plants and animals, modern populations have largely lost the knowledge and skills necessary to survive without industrial food production. The social and political implications would be equally severe. The refugee crisis, triggered by a Toba-scale volcanic winter, would dwarf anything in recorded human history, as populations from the most severely affected regions attempted to migrate to areas with better survival prospects. The resulting competition for increasingly scarce resources would likely trigger conflicts that could escalate into warfare between nations desperate to secure food, water, and habitable territory for their populations. The complex international cooperation that characterizes modern global governance would face unprecedented stress as countries prioritize their own survival over international agreements and humanitarian obligations. Perhaps most importantly, the Toba catastrophe demonstrates that supervolcanic eruptions pose threats that operate on timescales far longer than most natural disasters. Earthquakes, hurricanes, and even major volcanic eruptions typically cause damage that can be repaired within years or decades. But supervolcanic winter effects can persist for decades, creating ongoing survival challenges that test the limits of human adaptability and resilience. Recovery isn't simply a matter of rebuilding damaged infrastructure. It requires surviving through years or decades of fundamentally altered environmental conditions while maintaining enough social cohesion and technological capability to eventually rebuild civilization. The study of the Toba catastrophe has revolutionized our understanding of human vulnerability to natural disasters and highlighted the importance of preparing for low-probability, high-impact events. While we can't predict exactly when the next supervolcanic eruption will occur, we know from the geological record that such events are inevitable over sufficiently long time periods. The question isn't whether humanity will face another Toba-scale catastrophe, but whether we'll be better prepared to survive it than our ancestors were 74,000 years ago. Understanding the Toba event provides crucial insights into both the scale of the challenge we might face and the types of adaptations and preparations that might improve our chances of survival as a species. Right now, as you're watching this video, one of the most sophisticated geological monitoring networks on Earth is keeping a constant vigil over the Yellowstone supervolcano, recording every tremor, measuring every subtle ground movement, and analyzing every gas emission that might signal an awakening of the sleeping giant below. This isn't science fiction or theoretical monitoring for some distant future threat. This is happening in real time, 24 hours a day, 365 days a year, because scientists know that when Yellowstone decides to stir from its 640,000-year slumber, we might have only weeks or months of warning, before one of the most catastrophic natural disasters in human history begins to unfold. The warning signs that scientists are watching for aren't subtle theoretical indicators. They're measurable, quantifiable changes that are already occurring, and some of them are happening at rates that are considered extremely alarming in geological terms. The most obvious and easily understood warning sign is seismic activity. The earthquakes that constantly shake the Yellowstone region as the massive magma chamber below adjusts to changing pressures and temperatures. What most visitors to Yellowstone don't realize is that this seemingly peaceful national park experiences between 1,000 and 3,000 earthquakes every single year. These aren't major, destructive earthquakes that make headlines. Most are so small that they can only be detected by sensitive seismographic equipment. But they represent the constant movement and adjustment of rock formations as they respond to the enormous heat and pressure generated by the magma system below. Every earthquake is essentially the Earth's crust, cracking and shifting as it tries to accommodate the tremendous forces at work beneath Yellowstone's surface. The pattern and intensity of these earthquakes provide crucial information about what's happening in the magma chamber. When earthquake activity increases significantly above baseline levels, it can indicate that magma is moving within the chamber, that new magma is being injected from deeper sources, or that the pressure within the system is changing in ways that could precede an eruption. In 2014, Yellowstone experienced the largest earthquake swarm in over 30 years, with more than 60 earthquakes occurring in a single week, including several magnitude 3.0 events that were strong enough to be felt by park visitors. While this swarm ultimately subsided without leading to an eruption, it demonstrated how quickly seismic activity can escalate and provided valuable data about how the Yellowstone system responds to changing subsurface conditions. Perhaps even more concerning than earthquake activity is the dramatic ground deformation that has been occurring across the Yellowstone caldera over the past several decades. Using incredibly precise GPS measurements and satellite-based radar interferometry, scientists can detect ground movements measured in fractions of inches across the entire caldera system. What they've discovered is that the Yellowstone landscape is literally breathing like a living organism, rising and falling in response to changes in the magma chamber below. Between 2004 and 2014, portions of the caldera floor rose by nearly 6 inches, a rate of ground deformation that's considered extremely rapid in geological terms and could indicate that the magma chamber is inflating as new molten rock is injected from below. This ground deformation isn't uniform across the caldera. Different areas are moving at different rates and sometimes in different directions, creating a complex pattern of bulging and subsidence that reflects the three-dimensional structure of the magma system below. The Sour Creek Dome, one of the two major resurgent domes within the caldera, has been particularly active, rising faster than surrounding areas and creating measurable changes in the slope and elevation of roads, trails, and lake shorelines within the park. This isn't a gradual, barely perceptible change. It's happening fast enough that scientists have had to recalibrate their monitoring equipment and update topographic maps to account for the changing landscape. The hydrothermal features that make Yellowstone famous are also serving as early warning systems for potential volcanic activity. The geysers, hot springs, mud pots, and fumaroles scattered throughout the park are essentially natural monitoring stations that provide real-time information about temperature, pressure, and chemical conditions in the shallow geothermal system. Changes in the behavior of these features, such as new hot springs appearing, existing geysers changing their eruption patterns, or increases in the temperature or gas emissions from thermal areas, can indicate that the underlying magma system is becoming more active. In recent years, scientists have documented several concerning changes in Yellowstone's thermal features, including the appearance of new hot springs, dramatic temperature increases in some existing thermal areas, and changes in the chemical composition of gases being emitted from fumaroles. One of the most sophisticated monitoring techniques involves analyzing the gases that are constantly being released from Yellowstone's thermal features. These gases provide a direct chemical fingerprint of conditions deep within the magma chamber, and changes in gas composition can indicate magma movement, temperature changes, or the injection of fresh magma from deeper sources. Scientists continuously monitor the ratios of different gases, including carbon dioxide, sulfur dioxide, hydrogen sulfide, and helium isotopes, looking for changes that might signal increasing volcanic activity. The helium isotope ratios are particularly important because they can distinguish between gases that originate from the shallow crust versus those that come from the deep mantle, providing insights into whether the magma system is being recharged from below. Recent gas monitoring has revealed some troubling trends. Carbon dioxide emissions from some areas of the park have increased significantly over the past decade, and the isotopic composition of helium being released from thermal features suggests an increasing contribution from deep mantle sources. This could indicate that the magma chamber is receiving fresh injections of extremely hot magma from the mantle plume below, potentially increasing the overall temperature and pressure within the system. While these changes don't necessarily mean an eruption is imminent, they represent exactly the type of warning signs that scientists would expect to see if the Yellowstone system were beginning to move toward a more active phase. The integration of all these monitoring techniques creates a comprehensive picture of a volcanic system that is very much alive and potentially becoming more active. Advanced computer models that combine seismic data, ground deformation measurements, gas emissions, and thermal monitoring are painting a picture of a magma system that is significantly larger and more dynamic than previously understood. The discovery of the lower magma chamber in 2015, containing an additional 11,000 cubic miles of molten and semi-molten rock, fundamentally changed scientists' understanding of the Yellowstone system and suggested that the potential for future eruptions might be even greater than previously estimated. But perhaps the most unsettling aspect of Yellowstone's current activity is how it compares to the warning signs that preceded other major volcanic eruptions around the world. Studies of eruptions at other volcanic systems have shown that the types of changes currently being observed at Yellowstone, accelerating ground deformation, increasing seismic activity, changes in gas emissions, and thermal anomalies, often occur in the months to years before major eruptions. While every volcanic system is unique, and the timeline for any potential eruption at Yellowstone remains highly uncertain, the current pattern of activity falls within the range of what scientists would consider possible precursory behavior. The challenge facing scientists is distinguishing between normal background variations in an active volcanic system and genuine precursory signals that might indicate an approaching eruption. Yellowstone has been showing signs of unrest for decades, with periods of increased activity followed by returns to more typical background levels. The ground deformation that occurred between 2004 and 2014 was followed by a period of subsidence as parts of the caldera floor began sinking back toward their previous elevations. This pattern of inflation and deflation might represent normal breathing of the magma system, or it could be part of a longer-term trend toward increased activity that will eventually culminate in an eruption. Modern monitoring technology has given scientists unprecedented insights into the behavior of active volcanic systems, but it has also revealed just how complex and unpredictable these systems can be. The sophisticated sensor networks deployed at Yellowstone can detect changes that would have been completely invisible to scientists just a few decades ago. But interpreting these changes and translating them into reliable eruption forecasts remains one of the most challenging problems in Earth sciences. The timescales involved in volcanic processes often don't align well with human planning horizons, and the complex interactions between magma chemistry, crustal stress, and potential triggering factors make it extremely difficult to predict exactly when or if the next major eruption might occur. What scientists can say with confidence is that Yellowstone is currently showing multiple indicators of an active and potentially evolving volcanic system. The combination of ongoing seismic activity, measurable ground deformation, changing gas emissions, and thermal anomalies represents exactly the type of warning signs that would be expected if the system were moving toward a more active phase. While none of these indicators necessarily means an eruption is imminent, they do suggest that Yellowstone deserves the intensive monitoring it's currently receiving, and that continued vigilance is essential for providing whatever advance warning might be possible if the sleeping giant does begin to awaken. The sobering reality is that even with all our sophisticated monitoring technology, we might receive only weeks or months of clear warning before a major eruption begins. This timeline is sufficient for emergency evacuation of the immediate area around Yellowstone, but it's nowhere near enough time for society to prepare for the global consequences of a supervolcanic winter. The warning signs we can detect are primarily local indicators of magma movement and pressure changes within the Yellowstone system itself, but the global climate effects of a major eruption would unfold over years or decades, long after the initial warning period has passed. When most people think about volcanic eruptions, they imagine lava flows destroying everything in their immediate path, perhaps some ash falling like gray snow for a few days, and then a relatively quick return to normal conditions once the eruption ends. This fundamental misunderstanding of how supervolcanic eruptions actually work represents one of the most dangerous gaps in public knowledge about natural disasters, because the real killer in a Yellowstone-scale eruption wouldn't be the lava, or even the initial ash fall. It would be the prolonged nuclear winter effect that could plunge the entire planet into years or decades of darkness, cold, and ecological collapse that makes the immediate volcanic destruction seem almost trivial by comparison. Unlike the hypothetical nuclear winter that scientists worry about in the aftermath of global thermonuclear war, a volcanic winter from a Yellowstone eruption is virtually guaranteed to occur based on the geological record, and its effects would be far more severe and long-lasting than most people can possibly imagine. The mechanism that creates a volcanic winter operates on principles of atmospheric physics that are both elegant and terrifying in their simplicity. When Yellowstone erupts, it won't just spew lava and ash in the immediate vicinity. It will inject massive quantities of sulfur dioxide and fine ash particles directly into the stratosphere, the layer of atmosphere that extends from about 6 miles to 30 miles above Earth's surface. This is crucial because the stratosphere is above the weather systems that normally wash particles out of the atmosphere through rain and snow. Once volcanic material reaches the stratosphere, it can remain suspended for years or even decades, circling the globe and creating a persistent haze that acts like a planetary sunscreen, reflecting incoming solar radiation back into space and dramatically reducing the amount of sunlight that reaches Earth's surface. The sulfur dioxide component of volcanic emissions is particularly insidious because it undergoes chemical reactions in the stratosphere that make it far more effective at blocking sunlight than the original gas. When sulfur dioxide molecules encounter water vapor and other chemicals in the upper atmosphere, they form tiny droplets of sulfuric acid that are incredibly efficient at scattering and reflecting sunlight. These sulfuric acid aerosols are so small, typically less than 1 micrometer in diameter, that they remain suspended in the stratosphere for extended periods, creating a reflective haze that can cover the entire planet. The 1991 eruption of Mount Pinatubo in the Philippines provides a perfect example of this process in action, though on a much smaller scale than what we would expect from Yellowstone. Pinatubo ejected approximately 20 million tons of sulfur dioxide into the stratosphere, creating a global haze that reduced incoming solar radiation by about 2 to 3% and cooled global temperatures by approximately 0.5 degrees Celsius for nearly 2 years. This might sound like a relatively small change, but the cooling effect was sufficient to temporarily offset global warming trends and create noticeable changes in weather patterns around the world. Agricultural regions experienced shortened growing seasons, reduced crop yields, and unusual weather patterns that caused billions of dollars in economic losses. Now consider that a major Yellowstone eruption would be roughly 1,000 times more powerful than Pinatubo, potentially injecting 20 billion tons or more of sulfur dioxide into the stratosphere, enough to create a volcanic winter far more severe than anything recorded in human history. The temperature drops associated with a Yellowstone-scale volcanic winter would be catastrophic for global ecosystems and human civilization. Climate models suggest that average global temperatures could drop by 3 to 5 degrees Celsius, with some regions experiencing temperature decreases of 10–15 degrees Celsius or more. These numbers might seem abstract, but they represent the difference between a world that can support modern agriculture and human civilization, and one that resembles the Ice Age conditions that our ancestors barely survived tens of thousands of years ago. To put this in perspective, the entire difference between current global temperatures and the peak of the last ice age is only about 6 degrees Celsius, meaning that a major volcanic winter could potentially trigger ice age conditions within a matter of months. The reduction in sunlight would be equally devastating for the photosynthetic processes that form the foundation of virtually all life on Earth. Plants depend on solar radiation to convert carbon dioxide and water into the sugars and starches that fuel their growth and reproduction. Even a 50% reduction in available sunlight would be sufficient to kill most crop plants and cause widespread die-offs in natural vegetation. More severe reductions could essentially shut down photosynthesis across vast regions of the planet, creating a cascade of ecological collapse that would work its way up through every level of the food web. The darkness wouldn't be uniform across the planet. Some regions might experience conditions similar to a heavily overcast day, while others could be plunged into a twilight gloom that persists for months or years. The duration of a volcanic winter represents perhaps its most terrifying aspect. because unlike other natural disasters that cause intense but relatively brief disruption, the atmospheric effects of a supervolcanic eruption can persist for decades. The sulfuric acid aerosols created by volcanic sulfur dioxide are remarkably stable in the stratosphere, where there are no weather systems to wash them out of the atmosphere. They gradually settle back to Earth or undergo chemical reactions that neutralize them. But this process occurs on timescales measured in years rather than months. The geological record suggests that major volcanic winters in Earth's past have lasted anywhere from 6 to 10 years for the most severe effects, followed by additional decades of gradually improving but still abnormal conditions. The agricultural implications of such prolonged darkness and cooling would be absolutely catastrophic for modern human civilization. Our current food production systems are finely tuned to operate within relatively narrow ranges of temperature and sunlight, and even small deviations from normal conditions can cause significant crop losses. A volcanic winter severe enough to reduce global temperatures by 3 to 5 degrees Celsius would make agriculture impossible across vast regions that currently produce the majority of the world's food. The American Midwest, which produces much of the world's corn and soybeans, would likely experience growing seasons too short and too cold to support these crops. Similarly, the wheat-producing regions of Canada, Russia, and Northern Europe would face conditions that could eliminate grain production entirely for multiple years. Even in regions that might theoretically remain warm enough for some types of agriculture, the reduced sunlight would create insurmountable challenges for crop production. Most food crops require specific amounts of solar radiation to complete their growth cycles and produce viable harvests. Rice, wheat, corn, and other staple grains are particularly vulnerable to light reduction because they depend on intensive photosynthesis during critical growth phases to accumulate the starches that make them valuable as food sources. Laboratory studies have shown that even modest reductions in available light can cause dramatic decreases in crop yields, while severe light reductions can prevent crops from completing their growth cycles entirely. The cascading effects of agricultural collapse would extend far beyond simple food shortages. Modern civilization depends on complex supply chains that transport food from agricultural regions to population centers around the world. The failure of major agricultural regions would trigger a domino effect of shortages, price increases, and social instability that could overwhelm governments' ability to maintain order and distribute remaining food supplies. Countries that currently export food to global markets would likely halt those exports to preserve supplies for their own populations, creating international tensions and potentially triggering conflicts over remaining agricultural resources. The livestock industry would face equally severe challenges, as the animals that provide much of the world's protein depend either directly on grass and other vegetation, or indirectly on grain crops that would be devastated by volcanic winter conditions. Cattle, sheep, pigs, and poultry all require substantial amounts of feed to maintain their populations, and the collapse of grain production would make it impossible to sustain current livestock numbers. Mass culling of animals would become necessary within months of the eruption, providing a temporary surge in available meat, but ultimately leading to the collapse of protein production systems that currently feed billions of people. The ocean ecosystems that provide much of the world's fish and seafood would also be severely impacted by the reduced sunlight and altered weather patterns associated with volcanic winter. Phytoplankton, the microscopic organisms that form the base of marine food webs depend on sunlight for photosynthesis, just like terrestrial plants. A significant reduction in ocean productivity could trigger collapses in fish populations that would eliminate another crucial source of protein for human populations. The cooling of ocean temperatures could also alter ocean currents and weather patterns in ways that would further disrupt both marine ecosystems and the terrestrial climate systems that depend on ocean circulation. Perhaps most troubling is the potential for feedback effects that could prolong or intensify the volcanic winter beyond what the initial eruption alone would cause. As vegetation dies and forests collapse, the dead plant material could release stored carbon dioxide back into the atmosphere, potentially triggering additional climate changes. The cooling effect of volcanic aerosols could also trigger the formation of ice sheets in northern latitudes, creating highly reflective surfaces that would bounce additional sunlight back into space and perpetuate cooling conditions even after the volcanic aerosols begin to settle out of the atmosphere. The psychological and social effects of living under darkened skies for years would add another dimension of challenge to surviving a volcanic winter. Human psychology and physiology are adapted to natural cycles of light and darkness, and the prolonged twilight conditions could trigger widespread depression, seasonal affective disorder, and other mental health challenges that would complicate efforts to maintain social cohesion during an already catastrophic period. The stress of constant food shortages, combined with the psychological effects of unnatural lighting conditions, could undermine the social cooperation that would be essential for surviving such an extended crisis. The volcanic winter, following a Yellowstone eruption, wouldn't simply make farming difficult. It would trigger a complete collapse of Earth's interconnected ecosystems, unraveling billions of years of evolutionary relationships in a matter of months, and creating a domino effect of extinction that could fundamentally alter the trajectory of life on our planet. When we talk about ecosystem collapse in the context of a supervolcanic eruption, we're not discussing the loss of a few endangered species or the degradation of some natural habitats. We're looking at the potential breakdown of the basic biological processes that support all complex life on Earth, from the microscopic organisms that produce oxygen to the apex predators that regulate entire food webs. The scale and speed of this ecological catastrophe would be unprecedented in human history and could create changes to Earth's biosphere that persist for millennia after the volcanic winter finally ends. The foundation of virtually every ecosystem on Earth rests on photosynthesis, the process by which plants, algae, and certain bacteria convert sunlight, carbon dioxide, and water into the organic compounds that fuel all other life forms. This isn't just an academic detail about plant biology. It's the fundamental mechanism that captures energy from the sun and makes it available to every other living organism on the planet. When a Yellowstone eruption blocks 50 to 90% of incoming sunlight for years at a time, it doesn't just make individual plants grow more slowly. It begins shutting down the primary energy source that supports the entire web of life on Earth. The implications cascade through every level of biological organization, from individual organisms struggling to survive in a darkened world to entire biomes collapsing as their foundational species disappear. Forests would be among the first ecosystems to show visible signs of collapse, and their destruction would accelerate the global catastrophe in terrifying ways. Trees, which can live for decades or centuries under normal conditions, are surprisingly vulnerable to prolonged light reduction because they depend on consistent photosynthesis to maintain their massive structures and complex root systems. Within months of a major eruption, forests across the planet would begin showing signs of stress, leaves yellowing and falling, branches dying back, and entire trees beginning to weaken as their energy reserves are depleted faster than they can be replenished. The death of forests wouldn't happen gradually or peacefully. It would be accompanied by massive wildfires as stressed and dying trees become increasingly susceptible to ignition, creating enormous blazes that would pump additional smoke and particulates into an already darkened atmosphere. The collapse of forest ecosystems would eliminate habitat for countless species that depend on trees for food, shelter, and breeding sites. Birds that nest in forest canopies would find themselves without suitable nesting sites just as the insects and small animals they feed on begin disappearing due to the loss of plant life. Large mammals, like deer, elk, and bears that depend on forest vegetation, and the smaller animals that live in forest ecosystems, would face starvation as their food sources vanish. The complex relationships between predators and prey that have evolved over millions of years would unravel in a matter of seasons, creating unpredictable population crashes and behavioral changes that could destabilize ecosystems even further. Grassland ecosystems, which cover vast areas of the planet and support much of the world's remaining large mammal populations, would face their own unique challenges during a volcanic winter. Grasses are generally more resilient to environmental stress than trees because they store energy in underground root systems and can regrow from these roots even after the above-ground portions die. However, the prolonged cold and darkness of a volcanic winter would eventually overwhelm even these adaptations, causing grasslands to enter a state of dormancy that could last for years. The animals that depend on grasslands, including the cattle, sheep, and other livestock that provide much of humanity's food supply, would face mass starvation as their primary food source becomes unavailable. Perhaps most critically, the collapse of plant communities would trigger a breakdown in soil ecosystems that could have consequences lasting far beyond the volcanic winter itself. Healthy soils are incredibly complex ecosystems containing billions of microorganisms, fungi, insects, and other small creatures that work together to decompose organic matter, cycle nutrients, and create the fertile conditions that support plant growth. When plants die en masse during a volcanic winter, the soil organisms that depend on them for food and habitat also begin to disappear. The fungi that form symbiotic relationships with plant roots, helping them absorb nutrients and water, would lose their plant partners and begin dying off. The bacteria that fix nitrogen from the atmosphere, making it available to plants in a form they can use, would lose the plant-derived compounds they need for energy and cease their crucial nitrogen cycling activities. The loss of these soil microorganisms would create a feedback loop that could prevent ecosystems from recovering even after sunlight returns to normal levels. Soils stripped of their living communities become compacted, poorly drained, and unable to support healthy plant growth. The nutrients that plants need, nitrogen, phosphorus, potassium, and countless trace elements, would become locked up in forms that surviving plants can't access, creating desert-like conditions even in areas that previously supported rich ecosystems. The process of rebuilding these soil communities is measured in decades or centuries, meaning that the ecological effects of a Yellowstone eruption could persist long after the volcanic winter ends. Marine ecosystems would face their own catastrophic collapse as the volcanic winter progresses, beginning with the microscopic organisms that form the foundation of oceanic food webs. Phytoplankton, tiny floating plants that produce roughly half of the oxygen in Earth's atmosphere, while converting dissolved carbon dioxide into organic compounds, depend on sunlight just as much as terrestrial plants. The reduction in sunlight penetrating the ocean surface would cause massive die-offs of phytoplankton populations, eliminating the primary food source for zooplankton, small fish, and other marine organisms. The death of phytoplankton wouldn't just affect marine ecosystems. It would also reduce the ocean's ability to produce oxygen and absorb carbon dioxide, potentially exacerbating climate changes and creating additional stress for both marine and terrestrial life. The collapse of phytoplankton populations would trigger a cascade of extinctions throughout marine food webs that could eliminate many of the fish species that currently provide protein for billions of people. Small fish that feed directly on plankton would face immediate starvation, while larger fish that prey on smaller species would follow shortly afterward as their food sources disappear. Marine mammals like whales, dolphins, and seals that depend on fish and other marine organisms would face their own crisis as the ocean ecosystems they depend on collapse around them. The death of marine organisms would also create massive dead zones in the oceans as decomposing organic matter consumes available oxygen, creating conditions that could prevent the recovery of marine ecosystems even after other environmental conditions begin to improve. Coral reefs, often called the rainforests of the sea because of their incredible biodiversity, would be among the ecosystems most vulnerable to volcanic winter conditions. Corals depend on symbiotic algae living within their tissues to provide much of their energy through photosynthesis, making them extremely sensitive to changes in light availability. Even relatively small reductions in sunlight can cause corals to expel their symbiotic algae in a process called bleaching, and the severe light reduction associated with a volcanic winter would likely kill coral reefs across the planet within months. The loss of coral reefs would eliminate habitat for roughly 25% of all marine species, creating one of the largest mass extinction events in Earth's history and destroying ecosystems that provide food, coastal protection, and economic benefits for hundreds of millions of people. Freshwater ecosystems would face unique challenges as volcanic ash and altered precipitation patterns disrupt the delicate balance of lakes, rivers, and wetlands around the world. Volcanic ash falling into freshwater systems would change their chemistry, making water more acidic and introducing toxic compounds that could kill fish, amphibians, and aquatic plants. The reduced evaporation from cooler ocean temperatures would alter global precipitation patterns, potentially causing droughts in some regions while triggering floods in others. Wetlands, which serve as crucial habitat for countless species and help filter pollutants from water systems, would be particularly vulnerable to these changes because they depend on specific water levels and chemistry to maintain their ecological functions. The insects that pollinate plants and help decompose organic matter would face their own crisis as the plants and animals they depend on begin disappearing. Bees, butterflies, and other pollinators would lose their food sources as flowering plants die off, while the beetles, flies, and other insects that help break down dead organic matter would be overwhelmed by the massive amounts of dead plant and animal material created by ecosystem collapse. The loss of these crucial ecological services would further impair the ability of ecosystems to function and recover. creating additional barriers to ecological restoration once environmental conditions begin to improve. Perhaps most tragically, many of the species most likely to survive the initial volcanic winter would be those that are already considered pests or invasive species in human-dominated landscapes. Rats, cockroaches, and other opportunistic species that can survive on a wide variety of food sources and tolerate harsh environmental conditions would likely persist, while more specialized species that depend on specific habitat conditions or food sources face extinction. This means that the post-volcanic world could be dominated by a relatively small number of hardy generalist species, creating ecosystems that are far less diverse and resilient than those that existed before the eruption. The timeline for ecosystem recovery following such a catastrophic collapse would be measured not in years or decades, but in centuries or millennia. The complex relationships between species that characterize healthy ecosystems develop over evolutionary timescales, and rebuilding these relationships after a mass extinction event requires the slow process of evolution to create new species and new ecological interactions. Some ecosystems might never fully recover to their pre-eruption complexity and diversity, instead stabilizing at lower levels of organization that lack the resilience and productivity of the original systems. The Yellowstone supervolcano thus represents not just a threat to human civilization, but a potential reset button for the entire evolutionary trajectory of life on Earth. Modern human civilization represents the most complex and interconnected social system that has ever existed on Earth, a delicate web of technological, economic, and social relationships that spans the globe and supports nearly 8 billion people in a lifestyle that would seem miraculous to our ancestors. Yet this same complexity and interconnectedness that makes our civilization so powerful also makes it extraordinarily vulnerable to the kind of catastrophic disruption that a Yellowstone supervolcano eruption would create. Unlike our hunter-gatherer ancestors who survived the Toba catastrophe 74,000 years ago, we've built our entire way of life on assumptions of stability, predictability, and continuous technological progress that would be shattered within days of a major volcanic eruption. The collapse wouldn't be gradual or manageable. It would be swift, comprehensive, and potentially irreversible, challenging the very foundations of everything we consider normal about human society. The immediate crisis would begin with the largest refugee disaster in human history, as potentially 100 million Americans living in the western United States would need to evacuate regions made uninhabitable by ashfall, toxic gases, and pyroclastic flows. This isn't a theoretical number pulled from academic models. It's based on the documented ash distribution patterns from previous Yellowstone eruptions, which show that areas within 300 to 500 miles of the eruption site would receive ash deposits measured in feet rather than inches, making them essentially uninhabitable for extended periods. The ash wouldn't just be an inconvenience that people could sweep off their roofs and sidewalks. Volcanic ash mixed with water forms a concrete-like substance that clogs drainage systems, collapses buildings, and makes transportation impossible. The fine particles are also deadly when inhaled, causing a condition called silicosis that can permanently damage lungs and kill people within months of exposure. But where would these 100 million climate refugees go? The traditional assumption that people can simply move to unaffected areas breaks down when we consider that a Yellowstone eruption would create simultaneous crises across the entire planet. The volcanic winter effects would cause crop failures and social instability in every major population center on Earth, meaning that the regions that might normally provide assistance to disaster victims would be struggling with their own survival challenges. Countries that currently accept refugees during regional disasters would likely close their borders and focus on preserving resources for their own populations, creating a humanitarian crisis unlike anything in recorded history. The infrastructure that modern civilization depends on would begin failing within days or weeks of the eruption, creating cascading breakdowns that would be impossible to prevent or quickly repair. Volcanic ash is particularly destructive to mechanical systems because the fine, abrasive particles can infiltrate engines, electrical equipment, and ventilation systems, causing failures that multiply throughout interconnected networks. Commercial aviation would cease almost immediately, as jet engines cannot operate safely in ash-laden air. The grounding of air travel would eliminate the rapid transportation of people, goods, and emergency supplies that modern disaster response depends on, while also disrupting the global supply chains that deliver everything from medical supplies to computer components to grocery store shelves. Ground transportation would face similar challenges as ash accumulation makes roads impassable and damages vehicle engines, while the power grids that supply electricity to cities and industrial facilities would be vulnerable to both ash contamination and the massive increases in demand that would occur as people attempt to cope with the crisis using electric heating and lighting systems. The failure of electrical systems would trigger additional cascading failures in water treatment plants, telecommunications networks, and the computer systems that manage everything from banking to hospital patient records. Modern cities, which depend on constant inputs of food, water, energy, and information from external sources, would become essentially unlivable within weeks as these supply systems break down. The economic implications of such widespread infrastructure failure would be catastrophic beyond any historical precedent. The global economy is based on assumptions of continuous growth, stable currency values, and reliable transportation and communication systems that would all be invalidated by a Yellowstone eruption. Financial markets would collapse as investors realize that the fundamental assumptions underlying modern economic activity no longer apply, while the insurance industry would face claims that far exceed the total resources available to pay them. The interconnected nature of modern financial systems means that failures in one sector would rapidly spread to others, potentially eliminating the stored wealth that individuals and institutions depend on for survival. Agricultural systems that currently feed billions of people would face complete collapse as the volcanic winter makes farming impossible across vast regions of the planet. Unlike historical famines that typically affected specific geographic regions while leaving other areas capable of providing aid, a Yellowstone-induced agricultural collapse would be global in scope, making it impossible for unaffected regions to compensate for crop failures elsewhere. The highly specialized and mechanized nature of modern agriculture would make the crisis even worse, as farmers trained to operate sophisticated machinery and manage complex chemical inputs would find themselves unable to adapt quickly to the primitive farming techniques that might be necessary for producing any food at all under volcanic winter conditions. The social and political structures that maintain order during normal times would face unprecedented stress as governments struggle to maintain authority while being unable to provide the basic services that citizens expect. Democratic governments derive their legitimacy from the consent of the governed, But this consent assumes that the government can provide security, maintain order, and ensure access to basic necessities like food and shelter. When volcanic winter makes it impossible for any government to fulfill these basic functions, the social contract that holds societies together would begin to break down, potentially leading to civil unrest, revolution, or the collapse of entire nation-states. International cooperation, which is already fragile during normal times, would likely disappear entirely as countries prioritize their own survival over global humanitarian concerns or international law. The treaties and agreements that currently regulate trade, environmental protection, and military cooperation assume that all parties have surplus resources that can be directed toward common goals. Under volcanic winter conditions, when every country would be struggling to feed its own population and maintain basic infrastructure, the incentives for international cooperation would disappear, potentially leading to conflicts over remaining agricultural resources, fresh water supplies, and habitable territory. The military forces that governments depend on to maintain order and defend against external threats would face their own crisis as personnel struggle to maintain equipment and supply chains while dealing with the same food shortages and infrastructure failures affecting the rest of society. Military bases and equipment require enormous inputs of fuel, spare parts, and technical expertise to remain operational, and the breakdown of industrial systems that produce these inputs would gradually degrade military capabilities, even as the need for maintaining order increases. The result could be a period of widespread lawlessness as traditional authority structures lose the power to enforce their decisions. Medical systems that currently provide sophisticated healthcare to billions of people would be among the first to collapse under the stress of volcanic winter conditions. Hospitals depend on constant supplies of electricity, clean water, medical supplies, and pharmaceuticals to function, while medical personnel need reliable transportation and communication systems to coordinate patient care. The failure of these supporting systems would eliminate access to medical care for most of the population, just as health challenges increase due to malnutrition, exposure to volcanic ash, and the stress-related illnesses that would become common during such an extended crisis. The loss of modern medical care would dramatically increase mortality rates from conditions that are easily treatable under normal circumstances, adding another dimension to the humanitarian catastrophe. Perhaps most disturbing is the realization that modern humans have lost most of the survival skills that enabled our ancestors to survive previous global catastrophes. The vast majority of people living in developed countries have never grown their own food, built their own shelter, or produced their own clothing, instead depending on complex supply chains and specialized professions to provide these necessities. When these systems fail, most people would lack the knowledge and skills necessary to meet their basic survival needs, creating a situation where even those who survive the immediate effects of the volcanic winter might not be able to sustain themselves during the years-long recovery period. The psychological impact of watching modern civilization collapse would create additional challenges for maintaining the social cooperation that would be essential for group survival. Humans are psychologically adapted to living in stable social groups with predictable hierarchies and shared cultural norms. But the breakdown of familiar institutions and the stress of constant survival challenges could trigger widespread depression, anxiety, and social dysfunction that would impair people's ability to work together effectively. The loss of familiar entertainment, communication systems, and social structures that normally provide meaning and purpose to people's lives could create a crisis of morale that would be almost as dangerous as the physical challenges of surviving in a post-volcanic world. Education systems that currently pass knowledge from one generation to the next would largely disappear as schools close and teachers focus on their own survival, potentially creating a lost generation of children who grow up without access to the accumulated knowledge and skills that previous generations took for granted. The libraries, databases, and cultural institutions that preserve human knowledge and creativity would be vulnerable to physical destruction and neglect, potentially eliminating centuries of accumulated learning and artistic achievement. Even if some communities manage to survive the volcanic winter, they might emerge into a world that has forgotten much of what previous generations knew about science, technology, and culture. The urbanized lifestyle that currently characterizes modern civilization would become completely unsustainable under volcanic winter conditions, potentially forcing a return to agricultural and rural lifestyles that most people no longer understand how to manage. Cities, which currently house more than half of the world's population, would become death traps as their concentrated populations exhaust available food supplies while being unable to produce any food locally. The migration from urban to rural areas would create conflicts between city refugees and rural populations over access to land, water, and other resources necessary for survival, potentially leading to violence and social breakdown that would further complicate recovery efforts. The most haunting question that keeps volcanologists awake at night isn't whether Yellowstone will erupt again. The geological evidence makes it clear that another catastrophic eruption is virtually inevitable over long enough timescales. The question that drives urgent scientific research and emergency planning discussions is far more immediate and terrifying. When might it happen? And how much warning will we have? This timeline question represents one of the most challenging problems in Earth sciences because supervolcanoes operate according to their own incomprehensible schedules, following geological processes that unfold over hundreds of thousands of years, while being influenced by factors so complex and interconnected that even our most sophisticated computer models struggle to make reliable predictions. The brutal truth is that we're essentially trying to predict the behavior of a system so massive and complex that it makes weather forecasting look simple by comparison. The statistical approach to predicting Yellowstone's next eruption provides both reassurance and deep unease in roughly equal measures. Based on the geological record, major caldera-forming eruptions at Yellowstone have occurred roughly every 600,000 to 800,000 years, with the three known supereruptions happening 2.1 million, 1.3 million, and 640,000 years ago. This pattern suggests an average interval of about 725,000 years between major eruptions, which would seem to indicate that we're not yet in the danger zone since we're currently only 640,000 years past the most recent event. However, this statistical comfort is undermined by the realization that volcanic systems don't operate like clockwork, and the intervals between eruptions show significant variation that makes any precise prediction impossible. The gap between the first and second eruptions was 800,000 years, while the gap between the second and third was only 660,000 years, a variation of 140,000 years that represents a margin of error larger than the entire span of human civilization. Even more unsettling is the growing body of evidence suggesting that Yellowstone's eruptive behavior might be changing in ways that make historical patterns less reliable as guides to future activity. Detailed analysis of the geological record shows that each successive eruption has been more powerful than the previous one, with the magma chamber apparently becoming more efficient at accumulating and storing the enormous volumes of molten rock necessary for supervolcanic eruptions. This trend toward increasing power could also indicate that the intervals between eruptions are shortening, as a more efficient magma system would require less time to build up the pressure and volume necessary to trigger a catastrophic eruption. Some researchers have proposed that we might be entering a more active phase of Yellowstone's eruptive cycle, driven by changes in the deep mantle plume that feeds the system, or by modifications to the crustal structure above the magma chamber that alter how pressure builds within the volcanic system. The current level of activity at Yellowstone adds another layer of complexity to any timeline predictions, because the volcanic system is clearly not dormant in the way that truly inactive volcanoes are. The ongoing seismic activity, ground deformation, changes in hydrothermal features, and evolving gas emissions all indicate that the magma system is very much alive and potentially evolving toward some future state that could include renewed eruptive activity. The challenge for scientists is distinguishing between normal background variations in an active volcanic system and genuine precursory signals that might indicate an approaching eruption. The dramatic ground uplift that occurred between 2004 and 2014, followed by a period of subsidence, could represent normal breathing of the magma chamber or the early stages of a process that could eventually lead to an eruption. Recent technological advances have revealed that the Yellowstone magma system is far more complex and dynamic than previously understood, which makes timeline predictions even more challenging. The discovery of the lower magma chamber in 2015, containing an additional 11,000 cubic miles of molten and semi-molten rock, fundamentally changed scientists' understanding of the scale and behavior of the Yellowstone system. This lower chamber appears to be where magma from the deep mantle plume first accumulates before rising into the shallower reservoir that feeds the surface thermal features, creating a two-stage system that could behave very differently from the single-chamber model that scientists previously used for making predictions about future eruptive activity. The complex interactions between these multiple magma reservoirs make it extremely difficult to interpret the warning signs that scientists can currently observe. Seismic activity could indicate magma movement between the chambers rather than preparation for an eruption, while ground deformation might reflect pressure changes in the lower reservoir that don't necessarily translate to increased eruption risk in the near term. Gas emissions could signal the injection of fresh magma from the mantle plume, which might increase long-term eruption risk, but not provide any clear indication of when that risk might become reality. The sophisticated monitoring networks deployed at Yellowstone can detect changes that would have been completely invisible just a few decades ago. But translating these observations into reliable eruption forecasts remains beyond current scientific capabilities. International comparisons with other volcanic systems provide some insights into possible warning timelines, but they also highlight the unique challenges posed by supervolcanoes. Most documented volcanic eruptions have been preceded by clear precursory signals: increased seismic activity, ground deformation, changes in gas emissions, and thermal anomalies that develop over periods ranging from weeks to years before the actual eruption begins. However, Most of these examples come from much smaller volcanic systems that don't provide perfect analogies for how a supervolcano might behave. The few historical examples of very large volcanic eruptions, such as the 1815 Tambora eruption in Indonesia, showed precursory activity for several months before the main event. But even Tambora was orders of magnitude smaller than what a Yellowstone supereruption would represent. The Yellowstone Volcano Observatory, which continuously monitors the volcanic system using arrays of seismometers, GPS stations, gas sensors, and satellite imagery, operates under the assumption that a major eruption would likely be preceded by clear warning signs that would develop over weeks to months rather than years to decades. This timeline assumption is based partly on observations from other volcanic systems and partly on theoretical models of how magma chamber dynamics might change as the system approaches an eruptive state. However, the scientists running these monitoring programs are the first to acknowledge that their assumptions could be wrong and that the actual warning period could be much shorter or much longer than their current planning scenarios anticipate. The possibility of a shorter warning period is particularly concerning because it would leave insufficient time for large-scale evacuation and emergency preparation. If clear precursory signals only develop over periods of weeks rather than months, the logistical challenges of evacuating potentially 100 million people from affected areas would be essentially insurmountable using current emergency management capabilities. The transportation infrastructure necessary to move such enormous numbers of people simply doesn't exist, and the destination areas that could accommodate such massive population movements haven't been identified or prepared. Even with months of warning, organizing and executing an evacuation on this scale would represent the largest logistical undertaking in human history. Conversely, the possibility of a much longer warning period, with clear precursory signals developing over years or decades, would create different but equally challenging problems. Maintaining emergency preparedness and public attention over such extended periods would be extremely difficult, as people tend to become complacent about threats that don't materialize within expected timeframes. The economic costs of maintaining elevated alert levels for years would be enormous, potentially causing more disruption than the volcanic threat itself. False alarms and changing scientific assessments could undermine public confidence in emergency management authorities and make it more difficult to mobilize effective responses when genuine emergency conditions finally develop. The scientific community has struggled with the communication challenges inherent in discussing Yellowstone's timeline uncertainties without either causing unnecessary panic or creating dangerous complacency. Public statements about Yellowstone risk often emphasize that an eruption is not expected in the foreseeable future, based on the statistical analysis of historical eruption intervals and the current level of volcanic activity. However, these reassuring messages must be balanced against the reality that supervolcanic eruptions are low probability, high-impact events that could occur with relatively little warning, regardless of what statistical models suggest about their likelihood. Recent advances in volcano monitoring technology and computational modeling are gradually improving scientists' ability to understand and potentially predict volcanic behavior, but these improvements are incremental rather than revolutionary. Machine learning algorithms can now process the enormous data sets generated by modern monitoring networks to identify subtle patterns that might precede eruptive activity, while improved computer models can simulate magma chamber dynamics with increasing sophistication. However, these technological advances are still constrained by the fundamental challenge that volcanic systems are incredibly complex, with behaviors influenced by factors ranging from deep mantle dynamics to surface weather patterns that interact in ways that are difficult to predict or model accurately. The timeline question also intersects with broader issues of risk management and emergency preparedness that extend far beyond the scientific community. Government agencies responsible for public safety must balance the costs and disruptions of emergency preparations against the uncertain probability of a volcanic catastrophe, while also considering the many other natural and human-made threats that compete for attention and resources. The general public must somehow process information about a threat that is simultaneously inevitable over long time scales and unpredictable over the time scales that matter for personal and family planning. The result is a complex dance of scientific uncertainty, risk communication, and emergency preparedness that plays out against the backdrop of a sleeping giant that could awaken at any moment or remain dormant for thousands more years. Ultimately, the timeline question forces us to confront the uncomfortable reality that some aspects of our planet's behavior remain fundamentally unpredictable despite our technological sophistication. We can monitor Yellowstone with unprecedented precision, model its behavior using the most advanced computer systems available, and study its history through increasingly sophisticated geological techniques. But we still cannot answer the basic question of when the next eruption might occur with any meaningful precision. This uncertainty is itself an important part of the Yellowstone story, reminding us that we live on a dynamic planet that operates according to its own schedule rather than human preferences or planning horizons. When faced with a threat as overwhelming as a Yellowstone supervolcano eruption, the human mind naturally searches for solutions, for some technological fix or engineering marvel that could neutralize the danger, or at least reduce its impact to manageable levels. Unfortunately, the brutal reality is that there is no asteroid deflection mission for supervolcanoes, no heroic last-minute intervention that could prevent or stop a catastrophic eruption once it begins. Unlike many of the existential threats that humanity faces, supervolcanic eruptions represent forces so vast and fundamental that they essentially transcend human technological capabilities, operating on scales of energy and time that make even our most ambitious engineering projects seem trivial by comparison. This doesn't mean we're completely helpless in the face of such a threat, but it does mean that our preparations must be fundamentally different from the technological solutions we might envision for other global catastrophes. The most ambitious theoretical approaches to managing supervolcanic risk involve attempts to directly intervene in the Yellowstone magma system itself. And while these ideas capture the imagination, they also illustrate just how limited our options really are. Some researchers have proposed drilling into the Yellowstone magma chamber to release pressure gradually, essentially creating controlled venting that might prevent the buildup of conditions that could trigger a catastrophic eruption. The concept is appealing in its simplicity. If dangerous pressure is building up underground, why not provide a release valve that allows some of that pressure to escape safely? However, the practical challenges of implementing such a system are staggering and potentially catastrophic in their own right. Drilling into a magma chamber containing thousands of cubic miles of molten rock at temperatures exceeding 1400 degrees Fahrenheit would require technologies that don't currently exist and might not be physically possible to develop. The drill bits, casing materials, and cooling systems necessary to penetrate miles of solid rock and then maintain an open pathway into a magma chamber would face conditions more extreme than anything encountered in current drilling operations. Even if such drilling were technically feasible, the act of penetrating the magma chamber could potentially trigger the very eruption it's intended to prevent by providing a new pathway for magma to reach the surface, or by altering pressure relationships within the chamber in unpredictable ways. Another theoretical approach involves large-scale geothermal energy extraction, designed to cool the magma chamber by removing heat more rapidly than it can be replenished by the mantle plume below. The idea would be to install massive geothermal power plants that could extract energy from the Yellowstone system while gradually reducing its temperature and eruptive potential. Such a system could theoretically provide enormous amounts of clean energy while also reducing volcanic risk, creating a win-win scenario that appeals to both energy planners and disaster preparedness experts. However, the scale of heat extraction necessary to significantly cool a magma chamber the size of Yellowstone's would require thousands of geothermal installations working continuously for centuries, and the technology for extracting heat efficiently from such deep, high-temperature sources remains largely theoretical. The more realistic approaches to preparing for a Yellowstone eruption focus on building resilience and adaptive capacity rather than trying to prevent the eruption itself. This means developing systems and capabilities that could help human civilization survive and recover from the global disruptions that would follow a supervolcanic catastrophe, even if we can't prevent the catastrophe from occurring. These preparations require thinking on multiple timescales simultaneously. Immediate emergency response capabilities that could save lives during the first weeks and months of a volcanic winter. Medium-term adaptation strategies that could help communities survive during years of disrupted climate and agriculture. And long-term recovery plans that could help rebuild civilization in a post-volcanic world. Food security represents perhaps the most critical area for preparation, given that agricultural collapse would be the primary mechanism by which a Yellowstone eruption would threaten global human survival. Current global food storage systems maintain reserves sufficient to feed the world's population for only a few months under normal consumption patterns, and these reserves would be quickly exhausted if agricultural production ceased across large regions of the planet. Building strategic food reserves capable of sustaining significant portions of the global population through years of reduced agricultural output would require coordinated international efforts on a scale comparable to wartime mobilization, involving not just the storage of vast quantities of preserved foods, but also the development of alternative food production systems that could operate under volcanic winter conditions. Seed banking and agricultural genetic preservation have become increasingly important as scientists recognize the need to preserve the genetic diversity that would be essential for rebuilding agricultural systems after a global catastrophe. The Svalbard Global Seed Vault in Norway, often called the Doomsday Vault, represents one example of this approach, storing seeds from crop varieties around the world in a facility designed to remain viable even under extreme environmental conditions. However, the current scale of seed banking efforts would need to be expanded dramatically to provide the genetic resources necessary for rebuilding agriculture after a supervolcanic disruption. And these seed banks would need to be distributed globally to ensure that some facilities survive whatever regional disasters might accompany a volcanic winter. Underground food production systems represent another promising avenue for preparation, as these facilities could potentially continue operating even under the reduced sunlight conditions that would characterize a volcanic winter. Hydroponic and aeroponic growing systems that rely on artificial lighting and controlled environments could theoretically maintain some level of food production even when surface agriculture becomes impossible. But scaling these systems to feed significant populations would require massive investments in infrastructure and energy systems. The energy requirements for artificial lighting sufficient to replace sunlight for photosynthesis are enormous, meaning that such systems would need to be coupled with reliable energy sources that could operate independently of weather conditions and supply chain disruptions. Communication and coordination systems that could function during and after a global catastrophe represent another crucial area for preparation. Modern civilization depends on complex information networks that would be vulnerable to the infrastructure failures and social disruptions that would accompany a supervolcanic eruption. But maintaining communication capabilities would be essential for coordinating emergency response, distributing resources, and maintaining social cohesion during extended crisis periods. This might require developing distributed communication networks that could continue operating even when centralized systems fail, as well as preserving crucial technical knowledge in formats that would remain accessible even if digital storage systems become unavailable. Medical preparedness for a volcanic winter scenario would need to address both the immediate health impacts of volcanic ash exposure and the longer-term health challenges that would result from malnutrition, social stress, and reduced access to medical care. Stockpiling medications and medical supplies would be important, but even more crucial would be developing medical technologies and treatment protocols that could operate effectively under resource-constrained conditions. Traditional medical systems that depend on complex supply chains, sophisticated equipment, and highly trained specialists would need to be supplemented by more resilient approaches that could provide basic health care even when modern medical infrastructure becomes unavailable. Education and knowledge preservation systems would be essential for ensuring that human technological and cultural achievements survive a period of civilizational disruption. Libraries, databases, and educational institutions that currently preserve and transmit human knowledge would be vulnerable to both physical destruction and social collapse during a volcanic winter, potentially creating a situation where surviving populations lose access to the accumulated learning of previous generations. Developing robust systems for preserving and transmitting essential knowledge, including not just scientific and technical information, but also cultural and artistic achievements, would be crucial for maintaining human civilization's continuity through a period of global catastrophe. Perhaps most importantly, preparing for a supervolcanic threat requires developing social and political systems that could maintain cooperation and coordination during extended periods of scarcity and stress. History shows that human societies are capable of remarkable cooperation during crisis periods, but also that prolonged hardship can lead to social breakdown and conflict that makes survival challenges even more difficult. Building social resilience through community preparedness programs, conflict resolution mechanisms, and governance systems designed to function under crisis conditions might be just as important as technological preparations for ensuring human survival through a volcanic winter. International cooperation would be absolutely essential for any effective response to a global catastrophe like a Yellowstone eruption. But current international institutions are designed for managing cooperation during normal times rather than coordinating responses to existential threats. Developing international frameworks for sharing resources, coordinating responses, and maintaining cooperation during global emergencies would require unprecedented levels of international coordination and agreement. But such frameworks would be essential for maximizing humanity's chances of surviving and recovering from a supervolcanic catastrophe. The psychological and social dimensions of preparing for such an overwhelming threat also deserve attention, as the mere knowledge that such catastrophes are possible can create anxiety and despair that undermine people's ability to engage constructively with preparedness efforts. Finding ways to discuss and prepare for low probability, high impact threats without creating paralyzing fear or dangerous complacency represents a significant challenge for risk communication and public education. The goal should be to foster realistic awareness of volcanic risks while also building confidence in humanity's ability to adapt and survive even under extremely challenging conditions. Ultimately, preparing for the unthinkable requires accepting that we live on a planet that is far more dynamic and unpredictable than our daily experience suggests, and that our technological civilization, for all its remarkable achievements, remains vulnerable to natural forces that operate according to their own logic rather than human preferences. This recognition doesn't need to lead to despair or fatalism, but it should inspire humility about our place in the natural world and motivate serious thinking about how to build resilience into our social, economic, and technological systems. The Yellowstone supervolcano may sleep for thousands more years, or it may awaken tomorrow. Either way, the exercise of preparing for such possibilities makes us better equipped to handle the many other challenges that face human civilization in an uncertain world. If this exploration of our planet's most terrifying geological threat has opened your eyes to the incredible forces that shape our world, make sure to subscribe to The Sleepy Cosmos for more mind-bending journeys through science and space. Hit that notification bell because you won't want to miss our next deep dive into the cosmic forces that govern our universe.